Hello, welcome back to the Philip J. Curry Dinosaur Museum Virtual Speaker Series, where we have paleontology guests call in for a presentation on science, fossils, and dinosaurs, and where the public will be able to ask questions live on YouTube. For the viewers at home, you can leave your questions in the comment section, and I'll read them to our speaker at the end of the talk. First off, we want to acknowledge that we are on the homeland of the many diverse First Nations and Métis people whose ancestors have walked this land since time immemorial. We are grateful to work, live, and learn on the traditional territory of Treaty 8. Today, Dr. Aaron LeBlanc will be presenting how to become a dinosaur dentist, making new discoveries by studying ancient teeth. Dr. LeBlanc got his bachelor's and master's of science degrees from the University of Alberta in his hometown of Edmonton. He then traveled across the country to do his PhD at the University of Toronto's Mississauga campus, where he learned how to turn fossil jaws and teeth into microscopic sections the thickness of a human hair. By studying the teeth of different kinds of living and extinct animals, Aaron combines histology, the study of tissues, with paleontology to understand how teeth have evolved over the last 300+ million years. He is now a Marie Curie postdoctoral fellow in the Faculty of Dentistry, Oral, and Craniofacial Sciences at King's College London, UK, where he continues to study the teeth of extinct animals like dinosaurs. Thank you, Dr. LeBlanc, for joining us today. And with that, I will let you take it away.
Great. Well, thank you very much for the kind introduction. I'm calling in from London today. It's, I guess, sort of the benefit of being able to do these online seminars is, I don't have to travel all the way back to my home province of Alberta, even though I'd like to. But I can at least present some of the stuff to you guys today about, some of the sort of my personal journey, I guess, in academia and how I became a paleontologist, but also just sort of a story about cross-pollination in different scientific disciplines. So, how to combine things like dentistry and oral biology with the study of paleontology and the study of dinosaurs and other extinct organisms. So, see if I can do it this way. There we go. I thought I would start with a brief introduction of who I am. You got a kind of an introduction to my degrees and where I went. Like many paleontologists, I was interested in dinosaurs since the age of probably 4 or 5. I don't even remember. And I'm from Edmonton originally, and I was lucky to grow up there next to the University of Alberta, where I could go and study paleontology for my undergrad. And that's the core of my scientific training, is being a paleontologist. I did my master's there after I did my bachelor's degree. And I became an expert at studying fossil organisms. Now, this is sort of my first disclaimer for you. I'm not a professional paleontologist specifically working on dinosaurs. I actually focus on a whole bunch of different things, and I'll talk about how that happened. But I do, my fair share of your stereotypical paleontology work, whether it be in the field or studying fossils in a museum. But after I did my master's degree in Edmonton, I realized I needed a bit of a change of academic scenery just to kind of broaden my perspectives. And one of the things I wanted to learn how to do was palaeohistology. And I would say that, even though I am a paleontologist, I also call myself a palaeohistologist. And when I got to the University of Toronto's Mississauga campus, I talked to my PhD advisor, Robert Rice, and I wanted to learn how to take fossil teeth and jaws and cut them open and turn them into these microscope slides that are, maybe 1/10 of a millimeter thick or less, and look at them under the microscope and look at the tissues that are preserved inside. And through that, I was lucky enough as well to have access to the Royal Ontario Museum and Professor David Evans' lab as well. And there I sort of honed this very hands-on skill of taking something like a fossil tooth, like in this example here, and learned how to turn that into a microscope slide. So there's sort of I call it a 6-step process to do this. You first encase them in a resin to help stabilize the fossil, because most fossils are very fragile. They can flake away and crumble very easily in this process. And then we take that embedded block and we use a special type of saw with a very, very thin blade that spins pretty slowly. It's also coated in industrial grade diamonds, and it essentially cuts really slowly through your sample. I think I've got some pictures here of the saw in action. So you can see the blade from the top down in the image on the left, and it's a really thin blade. These blades, you can actually bend them with your fingers, so you do have to be really careful handling these machines. And you line them up to be, as precise as you can to expose a surface that you want to look at eventually under the microscope. And from there, we take that cut surface, we glue it to a microscope slide. We have different sizes of microscope slides depending on what we're looking at. You let the glue harden, and then you cut it again on that same saw, and you make a section much thinner out of that. So you have this little kind of wafer stuck on that microscope slide. But even then, that's still too thick for you to put under a microscope, because light still doesn't pass through a sample. So we take this a step further. We then put that wafer stuck on a microscope slide across a grinding wheel. And we do this very slowly. In this example here, this machine, we pass it across that grinding wheel multiple times. It can take a long time, but you have to go very slowly because you don't want to go too fast and grind right through it. That does happen. And you do this until you can start to see light passing through the sample. And at that point, it's very thin. But even then, you're not finished. The final step is as much a science as it is an art, and it takes a lot of experience. You have to do the rest by hand, where typically what I would do during my PhD was take a glass plate like this one. I'd throw some special grinding powder that's suspended in water onto that glass plate, and then take my slide and carefully grind it with different grits of this powder to eventually get the slide to the thickness I want. And each slide's different. It depends on the fossil you're looking at. And basically is just keep going back to the microscope until you know that you've got a sample that you can work with. So to give you an example of what the finished product might look like, here's an example from a little fossil mammal jaw that I studied during my PhD. And just to give you some context, so it'll be a section taken about here on this little jaw. It's got 3 teeth in it. We're going to look at that one middle tooth there. And this is what the finished product looks like. It's actually quite similar to what you would see if you made a section from a modern mammal. So when people talk about fossils, sometimes as being like a petrified remains or it's turned to stone, that's not really true. Because when you get to this magnification under a microscope, you actually see the same tissues that you would if, from a modern sample. You see the spaces in the bone where the cells would have been, or the blood vessels. And you see the other different parts of the teeth, for example, like in this one here. And so palaeohistology is, it's a long word, but basically it's just the study of ancient tissues. And for me specifically, like I said, I'm not really an expert on dinosaurs per se, but I am someone who's very interested in studying teeth. And I'm interested in the evolution and development of the different tissues that make up teeth, the enamel, the dentine, and these things called periodontal tissues. And I'll talk about these 3 throughout this talk. And I've sort of tacked on another 100 million years since I started working on teeth. I would say I really do study a very long range of the evolution of teeth. Teeth are ancient structures that you can find across all vertebrate groups in some form or another at some point in their evolutionary history. And it's pretty spectacular to see how they've changed over that time, and sometimes how they've stayed the same. And that's what really interests me about them. So back to my personal journey, I did my PhD up until 2016. That's a while ago now. And then I boomeranged back to Edmonton, to my hometown, at the University of Alberta, where I did postdoctoral fellowship. So this is sort of a transition phase between PhD and trying to become a professor. And a bit more independence in my research. And I realized, I actually want to study the same dental tissues I was looking at in fossils, but in living things. And so there I also learned how to be a histologist. So someone who is studying modern tissues. And it's a great way to then compare to your fossils and sometimes literally fill in the gaps of what was going on with all the different cells that are helping make teeth in all these different groups. I'm just showing you some examples of the slides I was looking at during that time. So who am I? I mean, if I could shrink it down to a single term, I jokingly use the term dinosaur dentist. And no, I cannot give you any official clinical advice as a dentist. I have zero training as a dentist. And ironically, I'm not a specialist on dinosaurs per se, but they do have lots of very cool teeth. And so I've spent a lot of time looking at dinosaur teeth carefully under the microscope. But I'm interested in the whole diversity that we see in teeth in all these kinds of different animals and what they can tell us about the diet and about the evolution of these different groups. And where am I now? Well, it's funny, we can't really travel right now under a global pandemic, but the timing just happened to be that, and I'm very grateful for this funding through this Horizon 2020 program through the European Commission. I got this Marie Curie Fellowship to become a postdoctoral fellow at King's College in London. And this happened in late 2020. And so I did manage to move to London during that time and do the quarantine and everything. And there was a time a few months ago, I took this picture as I was walking along the Thames. And I realized that's, wow, I'm actually kind of lucky in this sense, because I got to move to a really cool city during this time and continue research that I really enjoy. And so I sent this picture to my family with these really professional looking labels. And just to show you where I work at Guy's Hospital as part of the Greater King's College London campus. And it's right across the street from the Shard, which is that enormous triangular building there. And it's also just down the street from Tower Bridge. And sometimes it's just kind of amazing to think that I'm here coming from a would-be paleontologist from Edmonton. So it's been fun, but it's kind of a big transition for me academically as well, because I come from this field of paleontology and from studying teeth of these different animals, and now I'm full on in a dentistry faculty, and I'm specifically in the Center for Oral, Clinical, and Translational Sciences. And so you might be wondering, what is a paleontologist doing in a center for dentistry, and what could they possibly offer to that kind of faculty? And I would say it's actually been a very intellectually rewarding experience already for me, and I think for my colleagues as well there, because it's something very different for both of us, because paleontology provides that evolutionary context for why teeth look the way they do in different species, including in humans. And it kind of gives you a much larger palette of different organisms and different kinds of teeth to study that you just don't find today. And so it can lead to some really fun avenues of research in oral biology to kind of, like I said, cross-pollinate between different disciplines. And let me give you an example. So one of the things that I've gotten interested in since I got here is this idea of restoring enamel. Now, imagine this here. This is a section through a tooth crown, a human tooth crown. I can tell you that this is a microscope slide that I made, and you're looking at it under a special microscope filter. And so the tissues are lighting up this color because of the orientations of the tiny nanoscopic crystals inside the enamel and the dentine here. This is a section that I made of my own tooth. And it's a wisdom tooth that I had pulled a few years ago. And I told the dentist, pull it out, hole if you can. It has to go. I couldn't, it was erupting in a weird way. It needed to come out. But it would make a great tool for talks like this. And it has been. So this is a great example here of why it's important that we take care of our teeth. So enamel is the hard white covering on our teeth that we brush every day. It's when you smile in the mirror, that's what you're looking at on your teeth, is the hard coating of that enamel. Hardest tissue in your body, it's about 96% mineral. That mineral is called hydroxyapatite. It's the same mineral in your bones. It's the same mineral in the underlying tissue, the dentine. But the difference is, unlike the dentine, your enamel isn't sensitive to things like hot or cold or anything like that. And that's because it doesn't contain any cells inside it. It doesn't contain any blood vessels or nerves. It's effectively a dead tissue once your tooth erupts into your mouth. And that's important because we grind our food against the enamel of all of our teeth. But enamel, because it's a dead tissue, cannot regrow and it cannot repair itself. And that's a problem in today's dental world. It's sort of the $1 million question in dentistry. Can we repair dentine artificially in some way? Because we lose it gradually over time. You can lose it through tooth abrasion, like on this tooth here. You can see the cusp has been worn down a little bit. Well, and of course we get cavities, and that's an example of chemical wear, where bacteria gets into spaces and starts to erode away at our hard enamel. And we can't repair that. We don't get it back. And one of the struggles with repairing it, I mean, we can work with that mineral, this hydroxyapatite. We can make layers of hydroxyapatite artificially, but it's really hard to make it in as complex a shape as we see in human enamel. So if you look at it really, really closely under high-powered microscopes, so if you look at the box in red, for example, if you were to make a cross-section through that enamel, you'd see that it's not just laid down in sheets, it's actually woven together into these individual bundles or threads that are called enamel prisms, and they're separated, each of them, by a layer of another type of enamel. And to make matters more complicated, our enamel can even weave together like a basket weave. These prisms can change orientations as they go through your enamel. And they do this across, its whole thickness. You end up with, up to 2 millimeters worth of very complicated and very hard and resilient dental tissue to work with. And that's important, right? Because it is probably this complex to prolong the life of this tissue for as long as possible. And trying to restore there's a lot of people trying to do this, trying to restore prismatic enamel. And it's really challenging. One of the most promising and striking ones that I've read about since I've been here is this study here that's looked at sort of these worn enamel samples where they were able to artificially regrow the parts in green, where they have these enamel crystals that are basically perfectly growing on top of these enamel prisms. So that's really promising. They grow about 2 micrometers of this artificially. But the problem is, as they tried to grow more of this, the enamel prisms disappear. And instead you end up with sort of these generic sheets of crystals, which is not the same as what we see in humans. And so the problem isn't making enamel artificially, it's making these enamel prisms, which is the problem. And the reason why that's so hard is because the cells that make our enamel make those prisms. So each individual thread of these enamel prisms is made by a single cell called a ameloblast. And your developing teeth are coated in ameloblasts on the outside, and each one is producing a single enamel prism. And of course, once your tooth pops into your mouth, that layer of ameloblasts disappears. And so we no longer have the capacity to make ameloblasts. So imagine how hard this is to do artificially if we don't even have the cells to work with. That's where my interests come in, because it turns out that reptiles are very different. They have the same cells, these ameloblasts that make enamel, but they don't make enamel prisms. Instead, they seem to lay down this sort of soup of proteins and different chemicals to help grow these same enamel crystals, but in completely different patterns. And the really cool thing about this is that we can study the enamels of different kinds of reptiles to try and see if there are prismless types of enamel out there that might perform the same kinds of functions we need it to do if we were to try and synthesize it artificially in humans. And that's where we had a little bit of a bit of luck. When I got here, we were trying to think of different types of reptiles to look at and look at the structure, the internal structure of their enamel, and try and figure out, what it's like, how hard it is. Is it as hard as the prismatic enamel we see in humans? And we reached out to this crocodile zoo here in the UK. It's only about an hour and a half away from London, called Crocodiles of the World. It's the UK's only crocodile zoo, apparently. I had a chance to visit it recently. It's an absolutely amazing place, filled with some very beautiful crocodiles. And the staff at this zoo were gracious enough to donate a whole bunch of crocodile teeth from a bunch of different species to me for me to study. And crocodiles are great for this because there's several different species. They have different shaped teeth along their jaws depending on how they use them. And so it gave us a good start of diversity of different shapes and sizes of croc teeth to work with and to look at how the enamel in these different teeth is constructed. And so to give you an idea of what that looks like, just as an example here, this is one of the back teeth from an alligator, American alligator, that I've cut open using my standard histology techniques, and I polished it. And this is what it looks like up close. You can see they actually do have quite a bit of enamel that they pile on to those teeth. In this case, it's I think it's over 1 millimeter at the tip of this tooth. And you can see already that it's structured very differently on different regions of the tooth. And it's very different from what you see in humans. And just to show you what this looks like, here's some scanning electron microscope images of alligator enamel from a scientific paper showing you what that looks like. So they don't develop those discrete enamel threads or prisms, but nevertheless, there's a lot of different structure inside that enamel for us to study. And that's great because, as it turns out, even though we stereotypically think of reptile enamel as simple compared to human enamel, it actually is quite diverse. And there's different sort of arrangements of these crystals, even though they're not organized into these nice discrete units. You can get some pretty startling variation across different types of reptile teeth, depending on what they were used for, whether they were for catching slippery fish or for crushing hard shells or for cutting through meat. The enamel can look very different. And the really cool thing in talking with all of my dentist colleagues and oral biology colleagues here at King's is that by studying this, we're actually sort of moving the goalposts of what we can artificially grow in a lab in terms of artificial enamels, because we can already grow these types of enamels that look very similar to those we see in modern and fossil reptiles. So here's just some comparisons of some natural enamels that we see in reptiles on the left and some artificially grown ones in a few different studies that were trying to replicate human enamel and instead got these different structures. So it means that we're already much closer in being able to synthesize these types of enamels. It's just a matter of figuring out if any of these could be useful in the future. And the great thing about being in paleontology is once we've done this work with crocodilian teeth, and we're doing some pretty fun state-of-the-art techniques to study this in modern crocs and see how their enamel is organized in different dimensions and look at its chemistry as well, we can then go to the fossil record, because once you move into the fossil record, now you've expanded exponentially your palette of different types of teeth and different types of enamel you can look at to get ideas for what we call paleo-inspired enamels. in the future. So that sort of brings you to why I'm here now. And one of the major projects that I'm working on that I'm really excited about. It's early days still, but I'm hoping we'll have some more results soon. But I wanted to then take that, and because we're giving a talk for the Curry Museum, I wanted to sort of flip the script for the rest of this talk and talk about how dentistry and oral biology and the knowledge we gain from studying modern teeth can help inform us on what's going on in fossil teeth, mainly in dinosaurs. And this this thought process of moving from studying modern teeth to then extrapolating to dinosaur teeth is actually a very old practice. In fact, it goes back to the 1840s, and one of the pioneers of this sort of, again, cross-pollination of modern oral biology and paleontology has to be Sir Richard Owen. And Sir Richard Owen is famous in the paleontology circles, and I'll get to that reason why in a second, but he should be more famous, I think, in the dentistry realm, because through one of his books from 1840, it's called Odontography. It's this huge book. I think it's something like 600 or more pages long, has these amazing plates in it, drawings of what he was seeing under the microscope from his thin sections and fossils and modern things he was looking at. He was able to compare teeth and tooth tissues from everything from fish to amphibians to reptiles to mammals to fossils. And he realized that no matter what he looked at, teeth were constructed fundamentally from the same tissues every time. And he gave a name to one of those tissues that he still used today. And that one is called dentine. This is the part that makes up most of our teeth. It lies just underneath the enamel. It's the part that is sensitive to things like hot and cold. And he recognized that dentine's present in a whole bunch of different things. But the really fun little quirk, historical quirk about this book is if you look at the bottom left two images, those are drawings of thin sections he made of two dinosaur teeth. One's a meat-eating dinosaur, one's a plant-eating dinosaur. And he described them and talked about those tissues, but he never used the word dinosaur. In fact, if you look through the entire book, the word dinosaur isn't there. And that's because the word dinosaur wasn't invented until a year later by the same man, by Sir Richard Owen. And so he's doubly famous. And when he came up with the name in 1841 for dinosaur, he was thinking of them as some sort of extinct giant relatives of lizards. And that's where that name dinosaur comes from, right? It's dinos means fearfully great or terrible, and sauria means lizard. And of course, we know today that we love the name dinosaur, but it's actually a bit misleading, this idea of the terrible lizards, for two reasons. The first is they're not lizards. If you were to draw a family tree of dinosaurs relative to other things with teeth, they would nest quite nicely and quite closely with the crocodilians instead of the lizards. And more importantly, they're also not all extinct. There are, of course, an abundance of dinosaurs that are still alive today that escaped the bolide impact 65 million years ago, and those are the birds. And so we do have modern dinosaurs that we could look at to study. But of course, I'm a tooth guy. I really like studying teeth. Birds are among my least favorite animals to study because, of course, all modern birds have lost their teeth. There are fossil birds with teeth, which is great. But if we wanted to study modern dinosaur teeth directly, we can't do that because they just don't have any. So that's a problem. So if we want to study dinosaur teeth, we have kind of a two-step process that we can take. We can learn something about some modern animal and look at tooth development and evolution in their closest modern relatives, the crocodilians. And that's something I've done before, and obviously I'm continuing to do. And then we can use that and apply that knowledge to the study of dinosaur fossils directly, the ones with teeth. And we can literally fill in the gaps of what the cells were doing and the different soft tissues were doing that help maintain and develop the teeth in our favorite extinct animals. So I wanted to give you a little bit of a primer in croc dentistry, I will say, for a bit of this talk. And crocodilians are really great analogs to study for what's happening in dinosaurs, because they actually do a lot of things fundamentally similar to dinosaurs. One of the ones that's been my favorite to study over the last little while has been how croc teeth are anchored to the jaws. Croc teeth are very different from things like modern lizards. Modern lizards fuse their teeth to the jaws directly by a layer of bone. So there's this really, really hard connection between the teeth and the jaws. Instead, crocs are more like mammals, like you and I, in the fact that each tooth is suspended in its bony socket by a special ligament. So you can imagine the ligament acts like these tiny networks of little bridge cables that connect to the roots of each tooth. And they connect at this part called the cementum of the root. We have cementum as well. We do this exact same thing. And these just hold that tooth in that socket, and it provides a lot of flexibility to that connection between the teeth and the jaw, which is great for a croc, because if you've ever watched a nature documentary or been to a croc zoo and watched them eat, it's a very violent thing. And so there's a lot of piercing and grabbing and thrashing and twisting. And so having this flexible support is really beneficial for crocs. So we can ask, do dinosaur teeth do the same thing as crocs, or do they fuse their teeth directly to the bone like lizards do? And I've done this in multiple different studies, but here I'll just show one example from a tyrannosaur jaw that some colleagues and I sectioned a few years ago. So you're looking at a horizontal section through a single tooth socket in a tyrannosaur. And you see this every time you look at a dinosaur jaw and you section it. The teeth seems like they're magically floating in each tooth socket. And when you zoom in at that interface between the tooth root and the socket, there's usually a gap, or it's infilled like this one is here with sand and mud. So you have the speckled pattern is the sand grains, and then you have that black is just mud that fills in the gap between the tooth root and the surrounding socket bone. And that's always the case in every dinosaur I've seen. And so again, we can literally fill in the gap here by studying what happens in crocodilians. We know that there is a ligament that spans that space in modern crocodilians. And so we can infer that dinosaurs had this soft, flexible ligament system around each of their teeth that would have provided that cushion when they fed. And probably what happens is when they die, this ligament, which is soft tissue, completely decays and falls away, and we're left with a gap. And that gap, if we're lucky, the gap will get infilled with sediment like the one here, and that will essentially glue the tooth in place as it fossilizes. And that's important to recognize that, because as paleontologists, when you go out into the field, and my paleontology colleagues will confirm, oftentimes you'll find a dinosaur jaw. If you're lucky enough to find a dinosaur jaw, I should say, they'll be toothless. So it looks like all of the teeth have completely fallen out of the jaw. And that makes sense, because if you imagine that the only thing that holds them into the jaws in life is this soft ligament that is gone once the animals die and the soft tissues rot away, unless they get packed in there with sediment, they're very likely to just fall out. And that seems to be what happens in a lot of cases with fossil dinosaurs. A second thing that's really important to know about crocodilians, specifically about the crocodilians that I've worked with, as I mentioned, I've got a whole bunch of their teeth, and I really want you to know that none of the crocs from crocodiles of the world were harmed in the collection of their teeth. So I've got this great collection of teeth from different species in their care. None of these were pulled from their jaws or anything like that. They're very happily swimming along in their enclosures. And that's because all of the teeth that I have from them are shed teeth, the teeth that have just simply fallen out of their mouths that they were swimming around or feeding. And that's because you can think of crocodilians as basically tooth factories. They're continually making new teeth and replacing their old ones throughout their lives. Wouldn't that be great if we could do that? And so if you were to look at, say, a thin section through a crocodile jaw, like you're looking at on the left, oftentimes you see, you'll have the functional tooth, the old tooth sticking out of the mouth, but almost always underneath it, somewhere deep in the jaw, there's a new tooth that's growing slowly, that is slowly eating away at the base of at the root of the old tooth, and will eventually cause it to wiggle out, and you'll have a brand new tooth coming to replace it. And the really cool thing about studying modern crocs is you can even see the organ that makes teeth. And this really surprised me when I first started studying modern tissues, is if you want to imagine the structure that's making new teeth all the time in crocodilians, basically that's it. Or that red arrow is. It's this sort of ball of cells. It's shaped in 3D, it's sort of more of a string of cells that runs along the jaw. And this string of cells is continually starting that process of making a new tooth. In fact, even in this section I've shown you here, where it's made a new tooth, it's already in the process of making a second new tooth, indicate here with the blue arrow. And that's pretty cool because, as it turns out, I mean, we've essentially lost the ability to do that. We've lost that permanent little tooth-producing organ during the evolution of mammals. And so you can imagine, like my colleagues and friends sent me pictures of their kids at this very important stage in their lives when they underwent tooth replacement themselves. It's a really important step in our childhood because we only do this once. We replace a few of our teeth, and we only do it that one time, and we get our permanent set of adult teeth. And that's why we have to take such good care of them, because of course we end up with too many cavities, so we have to get a tooth pulled. You're not going to be able to replace it like you see in a crocodile. And most reptiles, I should say, in fact, most toothed vertebrates do that. They continually replace their teeth, continually make new ones. It's actually mammals that are kind of the freaks in that case. And we know from studying fossil dinosaurs that they too replace their teeth continually throughout their lives. And you can see this all the time in examples of fossils. There's new teeth poking out of the tooth sockets, ready to replace old ones. And they seem to be doing this quite frequently. And just to prove to you that, in these two examples, well, what if you could play devil's advocate and say, well, what if, we're just really lucky and we're only catching that one time that they replace each of their teeth, and maybe they were more like mammals. It's definitely not the case. If I go back to that section of a tyrannosaur jaw, the red arrow is pointing to the functional tooth, so the tooth that was in the mouth at the time the animal died, looking at it in that cross section. The two black arrows are showing you not one, but two new teeth that are developing deep down in this jaw to eventually replace the old ones. So it was like a tooth factory, continually making new teeth. And tyrannosaurs aren't even all that weird by dinosaur standards when it comes to tooth replacement. If you think of things like the long-necked dinosaurs, the sauropods, they can have, in this case, 1, 2, 3, 4 generations of teeth being produced behind each functional tooth in the jaw. And that's from a CT scan from a study. So you can imagine some dinosaurs are just making a staggering amount of teeth throughout their lives. And if we bring that back to paleontology, if you're walking around in the field in the Badlands of Alberta, this is one of the main reasons why shed or isolated dinosaur teeth are so common as fossils. And that has to do with the fact that simply one individual tyrannosaur or one individual hadrosaur or what have you would probably shed hundreds of teeth throughout its life, leaving potentially hundreds of fossils from that one individual, which is kind of a staggering thought if you think about how many fossil teeth are probably out there. So that's sort of that first step of why it's really important to study a good modern example like crocodilians to help us understand what's happening in dinosaurs. But for the last part of my talk, I wanted to go a bit deeper into a couple examples in dinosaurs that I've had a chance to work on. And this really has to do with some of the unique things we see by studying dinosaur teeth. And I want to give you two examples, one from a plant-eating group of dinosaurs, and then I'll end with everyone's favorite, I think, the meat-eating dinosaurs. And these are some pretty different, but I would say equally impressive adaptations for two completely different diets. And so you can imagine, even though modern crocodilians, they do have different shaped teeth along their jaws, like you saw from my pictures from crocodiles of the world, it's impressive. Dinosaurs take that idea of different shaped teeth and arrangements of teeth to an extreme. And so these two extremes I'm going to talk about today are going to be the tyrannosaurs and the theropod or meat-eating dinosaurs more generally, and the duckbill dinosaurs. And I want to start with the duckbill dinosaurs. This is an extreme example of a lot of the features I've talked about. And most people, I would imagine, are familiar with the duckbill dinosaurs. I get a lot of them in Alberta, also called the hadrosaurs. They get that duckbill name because of that sort of cropping bill that they have at the front that makes them kind of look a bit like a duck. They'd probably use to crop vegetation. But that's not the structure that was doing most of the work when it came to feeding. If you look inside the mouth of one of these hadrosaurs, they have these enormous dental batteries made of hundreds of teeth that are coalesced together that are making these huge grinding surfaces against which they were pulverizing their tough food, which we assume is tough plant material. And just to give you an idea of scale here, so one of those individual little diamond shapes would be a single hadrosaur tooth. And I spent a lot of time studying this because I was really interested in that. How does this structure form and how does that work? Because this is tooth replacement on steroids on top of clearly some other weird things going on to make a really efficient grinding surface. And so I made lots and lots of thin sections during my PhD. And to give you an idea of what that looks like inside one of these batteries, here you're looking at sort of a vertical section through a single column of teeth in a lower jaw, one of these dental batteries. And if you want to talk about tooth replacement, well, here's an example where at a single column, there are 6 generations of teeth at different stages of development, but also at different stages of tooth wear towards the top. So teeth 4, 5, and 6 were the ones that were actually being ground against the upper jaw and were being used. And they're all at different stages based on how old they are relative to each other. And so what you get when you section a duckbill dinosaur jaw like this, and these dental batteries, is you're getting a snapshot of the sequence of development of the birth and death of hadrosaur teeth. The really amazing thing about the grinding surface on hadrosaur teeth is that it's not, like I said before, a single tooth that's being ground down at a time in each of those columns. It's 3 teeth in this case at different stages of tooth wear. And because each of these teeth has the same arrangement of dental tissues, and because these dental tissues have different hardnesses, you end up with different rates of tooth wear, which will leave sort of ridges, tall ridges and basins along that tooth surface or that grinding surface that will be more efficient for grinding down tough plant material. And it's pretty amazing use of dental tissues to instead of trying to prevent tooth wear, what hadrosaurs were doing was taking advantage of it. And I really wanted to communicate what was going on inside these dental batteries. And so I reached out to a paleo artist at the Royal Ontario Museum, very talented paleo artist. And I told her, Danielle Dufault, that I wanted to create a visual graphic of a cutaway through a duckbill dinosaur dental battery that you could imagine in a dentist's office in the Cretaceous period. And so she more than delivered and created this graphic here. And so what I'm going to show you, this is from an upper jaw in this case. So we've flipped things. Just to show you the lifespan of a single hadrosaur tooth and the stages it goes through, because it's pretty amazing. So each tooth starts out by developing at the base of this big dental battery. And when you look at sections through the earliest teeth, they look like boomerangs. That's because they're cones that you've cut in half, so look like boomerangs. But they very quickly develop the hard tissues inside the teeth. So these hard tissues that are growing inwards, that's the dentine. This is supposed to be a very sensitive tissue because it surrounds the pulp, which is in humans, and well, anything with teeth, the pulp is the stuff inside your tooth that has all the blood vessels and nerves. So it's a lot of sensitivity associated with that. You can imagine it would be bad to expose that if you're a duckbill dinosaur. So to avoid that, the dentine closes off the inside of the tooth like a jacket zipper. And the walls of dentine eventually meet before the tooth reaches the grinding surface and completely cut off that vital sensitive pulp. The tooth essentially kills itself and loses its connection to the blood vessels. And what you have is a hard block of tissue that can be completely ground away without any sensation of, grinding away your tooth. And when I say completely grind away, I mean that hadrosaurs did completely grind their teeth away. So instead of like a crocodile where like they'll shed a tooth in their, think of that Crocodiles of the World, the zoo, where they were collecting the teeth out of the enclosures. Crocs and other animals will just drop their teeth and replace them with new ones. Hadrosaurs used every tooth right down to the tip of the root. And that's what I'm showing you here with this visual. This is thin sections through the upper and lower jaws put together, showing you the grinding surfaces. Each of them is made of 3 teeth at different stages of tooth wear. And the thing labeled T3 in both of those cases, those are just the tips of the roots of the oldest teeth in each of those series. And so you can see they were clearly grinding them completely away, using them right down to the little nubbins that were left. And I mean, that to add to that complexity, I mean, that was just sections through a single column of teeth in these dental batteries. Imagine what this looks like across the entire dental battery. So here, showing you Catherine Bramble and Matt Wasik, they're colleagues of mine that were helping with were doing these research projects as well at the same time as I was doing, basically. And they created these really stunning thin sections taken horizontally across these dental batteries. So now you're looking at what's going on. Each of these lines of teeth is a single column of teeth, and that's only half of that dental battery. And so you can imagine hundreds of teeth going through this rigmarole from early development all the way to grinding them completely away. All of this happening along the jaw in each of these duckbill dinosaurs, which is pretty amazing. So if you can't tell, I actually have a real soft spot for the plant-eating dinosaurs, especially the hadrosaurs, just because of how complicated that structure is. But that doesn't mean that the carnivorous dinosaurs didn't have their own secrets hidden inside their teeth that we could study. And so for the final bit of this talk, I wanted to talk about, I'm sure, many people's favorites, the theropods, or the meat-eating dinosaurs. So I think when we think of meat-eating dinosaurs, a lot of us will think of T-Rex and its kin, and we know them very well from their teeth. Their teeth can be slender blades, serrated like steak knives, or they can be more banana-shaped, like in Tyrannosaurus Rex for kind of a crushing and piercing bite. And it's probably true that that's how they use their teeth. And I think our best modern analog for how meat-eating dinosaurs fed, and we can think of as paleontologists, is actually what happens in Komodo dragons. And these are monitor lizards. They have no relationship to dinosaurs, and at least not like crocodilians do. Their lizards are much farther removed, evolutionarily speaking. But Komodo dragons feed in a really interesting way. They actually, if they have a food item that's much bigger than themselves, they'll often grab on to, if you watch a nature documentary, or if you've been fortunate enough to see them in the wild or at a zoo and it's feeding time, they'll grab on to their food item and they'll pull backwards. And that seems to be a very common behavior probably in meat-eating dinosaurs as well. And we know that because one of the reasons is that their teeth are extremely similar. So Komodo dragons, like the examples on the left here, their teeth are blade-like. They're kind of curved backwards. They're compressed in sort of in side directions to be like a blade. And along the cutting edges of that blade, you have these tiny bumps called denticles. And these act like the serrations on a steak knife to help them cut through meat as they do that sort of pullback or thrashing motion to tear chunks off to swallow. And you can imagine that something like a tyrannosaur, like an example on the right I'm showing you, when we cut open that cutting edge and we look inside the tiny bumps, the denticles on the cutting edge of this tooth, I mean, they're constructed in a very, very similar way to help them cut through meat. But there's a bit more to it. And this brings me to a study that was led by Dr. Kirsten Brink. She's now at the University of Manitoba. We did our PhDs together in the same lab at the University of Toronto Mississauga campus. We were interested in one very tiny but very key difference in meat-eating dinosaur teeth compared to, say, a Komodo dragon. And it relates to the two arrows I've given in the image on the right of the tyrannosaur tooth. So you're looking inside the cutting edge of this tooth, and each of those bumps there is a single denticle, a single bump along that cutting edge. So it's very small. And the blue arrow is pointing to this weird looking crack or channel that runs through the enamel and into the underlying dentine. And at the end of this channel, you always have, between every single one of these bumps along the cutting edges of these teeth, you have this weird looking gap with like a halo around it. And we weren't the first people to notice this. It's important to note that this doesn't happen in things like Komodo dragons. They don't have that structure. But oddly enough, when it was first observed in I believe it's the early 90s, it was thought that it was unique to tyrannosaur dinosaurs. But what Kirsten, myself, and our colleagues realized is it's actually an extremely common feature across almost all meat-eating dinosaurs. They all seem to have this weird crack-like structure between every single little bump along the cutting edge with this like hole at the end of it. And when it was first described in the early 90s, this whole structure was called an ampulla. And then we had sort of that kind of crack that I've labeled in blue. And one of the leading ideas about what this structure is and what it does is that it's a very unique crack stopping feature naturally developed inside the teeth of these meat-eating dinosaurs. So if you imagine you're driving along a gravel road and there's a car in front of you and it kicks up a rock and it hits your windshield, you end up with a crack. That crack can continue to spread along your windshield. One way to stop it is to actually drill a very tiny hole at the end of the crack. And what that does is it sort of dissipates the energy as that crack tries to split across the glass, and just stops the crack from continuing on from where that hole is. And that seems to be very similar to what's going on in these meat-eating dinosaur teeth. But what Kirsten and myself and others were really interested in is it the fact that there's a crack forming in between every single one of these tiny little denticles along each tooth, and then they have to develop this hole to stop cracks from spreading? Or is the crack actually a channel that develops naturally? And this hole is actually a natural gap that forms inside every single one of these meat-eating dinosaur teeth to just sort of prevent any of that from happening in the first place. And that seems like a very complicated question to ask, but remember, dinosaurs, like other reptiles, continually replace their teeth with new ones. And so all we had to do was to compare teeth that were erupted in the mouth, ones that the animal must have been using in life, to those that could be prepped out from deeper in the jaw that were still developing and hadn't been used. And we can ask, do we see that same structure in the older teeth, where we expect it to be, but do we also see it in the developing teeth that are still hidden deep inside the jaw? And so we compared that. We had two examples where we could do that. And one example was in a tyrannosaur and in Gorgosaurus. So here's the channel and the gap, the thing called the ampulla in Gorgosaurus. And here it is in another carnivorous dinosaur in Allosaurus on the right. And what about their new teeth? Well, it turns out their new teeth also have these structures developing in between every single one of these bumps along the cutting edges. So this is a feature that develops naturally inside the teeth of meat-eating dinosaurs. Presumably, we think to help dissipate those forces as these teeth are cutting into their prey items. And again, because we can rely on the really robust knowledge we have about how teeth form in modern things, we can do one final example where we sort of use development, principles of how teeth develop normally, and apply it to the fossil record to figure out how these unique structures formed. And so again, Danielle Dufault was gracious enough to give us take another challenge on to do one of these kinds of diagrams. And what we hypothesize is that when you have these little bumps forming on the cutting edges of each of these teeth, before any hard tissues are laid down, the cells that are sort of outlining the shape of the tooth first fold. And they fold deeply in between each of the denticles, each of those little bumps. And then the hard tissues, the dentine, begins to form first, as it does in every other tooth, really, every other reptile tooth. It then begins to form dentine around this gap. And that's why you end up with developing teeth inside the jaws that already have these gaps. And then the dentine continues to develop as the teeth get older before they've erupted into the mouth, though. Then the enamel gets added. And as the enamel continues to grow, it sort of hits this impasse along the furrow in between two bumps and leaves a channel in between in the enamel that leads down to that gap. And by the time the tooth erupts, you end up with that whole picture of this strange structure in between every single one of those bumps along the serrations. So that was a lot of tooth talk. And if you take anything away from this presentation, maybe next time you go to the dentist's office, you can chat with them about dinosaur or croc teeth and have something to chat about while they're checking out your teeth for cavities. And maybe you'll impress your dentist with some of the knowledge you have about dinosaur teeth and be able to talk to them about the same kinds of, using the same kinds of words they do, things like dentine and enamel and ligaments around the teeth and things like that. But I hope you at least sort of appreciate the value in this idea of interdisciplinary science. So taking ideas and concepts and knowledge from different fields and combining them to learn something new. In this case, learning something new about some of our favorite extinct animals, the dinosaurs. So with that, I have a huge number of people to thank. I mean, in no particular order, as well as some sources of funding I've had along my intellectual journey to where I am now in London. And so a huge thank you to them and to all the people that have helped me. And I know there's more that aren't on this list, and you know who you are, and I thank you as well for all your help. But specifically, I'd like to also thank you for listening and for the Curry Museum staff for inviting me to give a talk today. And so with that, thank you. If you'd like to follow me on Twitter, I do like to post an occasional Fossil Friday. You'll learn a lot more about teeth. That seems to be the thing I'm obsessed with these days. And I also blog. I recently bought a domain name. So if you want to check out some of the things I write about, obviously related to teeth, that's where you can find me. So I will stop there and I'll stop sharing, and I'd welcome any questions you might have.
Awesome, thank you, Aaron. That was wonderful. Yes, we are going to move into the question period. If anyone has any questions, you can type them in the sidebar, and I will read them out loud. First question, what is your favorite type of tooth?
Oh, yeah, okay. That is a tough question. What is your favorite type of tooth? You know what? I am a huge fan of the duckbill dinosaur teeth, mainly because they look so odd, and the fact that they just seem to kind of fill in their own pulp cavity with tissues and do all kinds of crazy things when they grind them. I really like them. Yeah, I mean, there's a whole bunch of different other ones out there that I could mention, but I would say that one's probably the leading candidate still. But I'm sure if you ask me probably a couple of years from now, I'll have a new favorite.
We'll have to ask you again next time we see you. James would like to know, if birds are descendants of dinosaurs, why do we know why they swap teeth for a beak?
That's a really, really good question. Why would they swap teeth for a beak? I mean, it must have something to do with their diet. I can't give you a concrete answer, but I will tell you this. I will tell you that they're not the only animals to do that, right? So another good example that I've never had the chance to study, but ancient turtles and the close relatives of turtles, they had teeth. There are groups of what we sometimes incorrectly call mammal-like reptiles, but the precursors evolutionarily to mammals. There are examples there even where they've lost teeth and replaced it with a beak. And in some of those examples, it might be related to eating plants. In others, yeah, I'm not really sure. That's a really good question.
Next question. What is the oldest tooth you've studied?
The oldest tooth I've studied. Probably, I've really gotten interested in the teeth of some of the earliest vertebrates. So these are fish, and they look superficially like fish you would see today. But when you look up close, a lot of these animals have teeth that are constructed very, very differently. They look very strange. And I'm interested, these animals are probably about 400 million years old or more. And they're really interesting because when you go that far back in time, it becomes really hard to connect the dots to figure out which tissues are evolutionarily the same as the ones you see in later animals like mammals or reptiles. And so it's been sort of this slow progression backwards for me. I've been working through, studying mammals, learning how their teeth work, and crocs and dinosaurs. And I just sort of keep moving backwards down that family tree. And who knows where that'll take me. But that's the oldest I've gotten to.
I guess that relates to our next question. What would you like to study next?
What would I like to study next? Well, without giving too much away, I've gotten really interested in snake teeth lately, mainly just because snakes, even though superficially their teeth you might think they look the same, they're kind of long and pointy. They do all kinds of really weird things with them. Some of it related to how they replace them, so how they get rid of the old ones and bring the new ones in is really, really strange. We've also gotten really interested in how they made venom fangs. For example, those are teeth that inject venom into their prey to paralyze and eat their prey. That is definitely a big one. Sharks, I really love studying sharks. I've been doing that for a couple of years now, still working out some of the features of their teeth. So yeah, it's all over the place right now. There's only one common thread, and that's teeth.
Next question. Do you have Or do any other animals have ampullae in their teeth, or is that feature unique to theropods?
Yeah, another great question. That channel and like hole in between each individual serration on theropod dinosaurs. So when it was initially described, it was thought that this was unique to tyrannosaurs. And then as Kirsten and all of us started looking at the thin sections she was making, we realized it was really, really common across meat-eating dinosaurs. I think we even saw it in some archosaurs that are outside of dinosaurs. But the big discovery on that front just came, we published on it just last year, at the end of last year, was the exact same structure in these things called gorgonopsians. And these are, again, sort of precursors evolutionarily to mammals. Not all that closely related to mammals. They were doing their own thing. They're very, very carnivorous animals. They had these serrated blade-like teeth along the jaws and usually these big sort of saber-like canines. When we looked at their teeth, they too, they have the exact same structure. So it's clearly serving a really important purpose in a lot of these carnivorous animals. And we might even see it in some other groups too.
Fascinating. What can you tell of tooth replacement rates from these different groups? Is there a way to see if the lifespan of a single tooth or how long it lasts from looking at the wear patterns?
Yeah, can we figure out how long a tooth lasts in a dinosaur or how quickly they replace them? I would say, yeah, we can get pretty close to guessing sort of in a relative sense how fast or how slowly a dinosaur is replacing its teeth. One of the ways that got a lot of traction in our field is this idea of counting growth lines inside teeth. And so if you imagine that, like the Tyrannosaur example, if you were to cut open a jaw of a Tyrannosaur, you can actually see growth lines in the dentine. And we think that there are daily growth lines inside the dentine. And so it'd be like counting tree rings, only instead of years, you're counting in days how frequently they're adding dentine. And you can imagine if you can do that for a functional tooth, and you can do it for a replacement tooth, you subtract the two, you get sort of a approximate rate at which they're adding new teeth. One of the challenges of that, in my opinion, it's actually a very common practice right now. One of the challenges with it, I think, is that it's hard to prove that these are daily lines that are being preserved in fossil teeth, because even when we study them in modern animals will leave, like you and I will leave growth lines in our dentine, but we may not do it daily. We might have some lines that are deposited daily, but for some reason, we have some that might be deposited 2 or 3 times a day. We have some that might be deposited once every 5 days. Mine might be different from yours. You might have some deposit every 7 days. So it's really, really tricky. But we think we can get sort of rough ideas, which ones are replacing them fast and which ones are replacing them slowly.
Very cool. You had mentioned once that enamel is gone, it's gone. Are there any current leads or research how to regrow it or recreate it?
Yeah, that's a really good question. So not really an expert in that field right now, but I will tell you it's been really cool to read about and listen to talks from scientists that are actively engaged in that research, and there are quite a few. One example is studying mice, because mice have these ever-growing incisors. They're continually pushing out their incisors, their uppers and lowers, and they're continually grinding them away at the tips. And deep down inside, at the bases of those teeth, you have cells that are continually turning into those enamel-producing cells and continually making enamel. So that might be a useful model to study to see if you can create the cells that are producing enamel. That's one avenue. And I know that there's a lot of other researchers that are also just trying to do this synthetically. They're trying to come up with different sort of compounds that they can use to relatively quickly make new enamel on a tooth that's already sticking out of the mouth in a patient. So far, as I've shown you, it's a challenging topic, but there seems to be these sort of stepwise advances happening all the time.
That would be very nice, especially for those of us that like sugar a little too much.
Yeah.
Next question. You mentioned that cross-pollination between fields of science. Are there any other sectors you would like to collaborate with, or fields that would be ideal for paleo to take a look at?
Yeah, I mean, there's a ton. For me specifically, a lot of the researchers I work with, while they might be dentists, a lot of them are also biomaterials specialists. So they look at things like implants. Implants is actually a big one in the labs that I work in, as well as different ways to tease apart the microstructure of different materials. Working with them has been great because I'll take a croc tooth or a dinosaur tooth, and they'll show me the techniques I can use, the same techniques they use, to look inside enamel and dentine at like almost the nano level, to recreate and reconstruct what's happening inside with all the individual crystals. And so that's great because I end up working with a lot of people who are essentially physicists. And so from that side, that's sort of one I'm starting to get into now that I never thought I would get into. But there's a lot of different other ones that I could talk about that paleontologists are always interacting with different disciplines to answer new and more challenging questions.
Awesome. Bit of a trivia question for you. Which animal has the largest tooth?
Oh, which animal has the largest tooth? That is a hard one. I'm going to say it's going to be something like, I have to think on the top of my head here, something like a mammoth. So imagine, the tusks of an elephant or a mammoth, those are teeth. Basically, a mature tusk is essentially it's an ever-growing tooth root. So the crown is gone. It's just sort of continually growing a root. That's a tooth, and it's absolutely enormous. You see the same thing in narwhals. So they're the whales with like a unicorn horn. That's a tooth, and it's huge. So it'd be something like that, I would guess.
Very cool. Yeah, I can't imagine anything much bigger than that.
Yeah, I'm gonna go. It's a safe bet. I'm gonna go with that.
I think. Oh, one more question. Would you rather cross-section a Krogan tooth or a thresher maw tooth?
Oh yeah, that's so this is a nerdy question, and I know who, I think I know who's asking me this, but that's my favorite video game. That's from Mass Effect. That's a great question. I don't know. I both would be awesome. That's whoever sent me that. Thank you for bringing that into it.
Thank you to James.
Perfect.
All right, I guess that concludes our question period. Thank you very much, Dr. LeBlanc. For those of you listening, join us again on Saturday, July 3rd at 3 p.m. as Mark Powers will be presenting the evolution of Eudromosauria and the biogeography that led to strong divergent trends. All right, thank you again.
Great, thank you.
Thank you to everybody for listening.